morning. Today I'd like to talk about arc length and lateral surface area. By arc length, I mean the following situation. We're going to have some sort of curve in the plane that starts at some specific point and ends at another point. And I just want to calculate the distance along the curve from the starting point to the ending point. And let me be very exact here. I'm talking about literally the distance that I would travel if I had to walk along that path, not the straight line distance that connects the endpoints. That would be easy. Now, you've probably noticed that we've been using the same trick as we calculate things over and over again, and we will continue to do so for the rest of this material. The idea is always take the situation that you're given and divide it up into many smaller, similar situations, which you can easily handle. Handle the easy cases, add up the results, and take the limit in some sense or the other. So that's exactly what we're going to do. We're going to chop our curve up into so small chunks that they look approximately straight. And then we're going to use the Pythagorean Theorem to calculate the actual distance that goes with each chunk. We'll add those up, and there'll be a little bit of fiddling around with how we do the limit exactly, but we'll see that shortly. The Pythagorean Theorem says, if I have a point and another point, if I want to calculate the distance between them, I take the amount that the horizontal changed, the amount that the vertical changed, take those two numbers, square them, and add them up. That's not the distance, it's the square of the distance. So if I want the distance itself, it's radical delta x squared plus delta y squared. As I said, we're going to do the same idea we did before. We will chop our situation, which in this case involves the length of the curve, into much smaller pieces, so small that I can regard each one as more or less straight, meaning that I can use the Pythagorean theorem to estimate the length of each individual piece. So I'm going to follow the same generic setup that we've been following for integrals. I'm going to divide my curve up into n smaller chunks. I'm going to think about chunk number I. I'll call the horizontal displacement delta x number I, the vertical displacement delta y number I. The length of that chunk is, using the Pythagorean theorem, easy to write down. The total length is going to be the sum of these individual lengths. This will approximate the total length of the curve. And then to get the arc length, I'll take the limit as the size of these chunks tend down to points in some sense or the other, which we haven't exactly specified yet. This almost looks like the definition of the integral of something, but the formatting is not right. I'm supposed to have the sum of some function of ci or xi, and then I'm supposed to have delta something on the outside, and this is not exactly how this looks, so we have to manipulate it a little bit. We won't be able to talk about very general curves until after we've talked about parametric equations. So for right now, we're going to have two situations to think about in regards to arc length and lateral surface area. One of them is the curve that we're talking about is a graph of a function in the usual familiar sense of the term. That is, y equals f of x, meaning if you give me an x, there's only one y to go with it. Or I could regard y as the independent variable and x as the dependent variable. I could have some function that tells me the x coordinate in terms of the y coordinate. For each y, there'll be one x to go with it. Really, the second picture is redundant. It's the first one flipped over with the variable renamed. But it's common in textbooks to cover both cases explicitly, so we'll at least mention that. Looking at the distance along chunk number I, this is the Pythagorean theorem again. What I'm going to do is, in each of those two terms, I'm going to factor out delta xi squared. When I do that to this first term, I'll just have a 1 left over. And when I do it here, I would have delta y squared over delta x squared, which I'm just going to write as the square of delta y over delta x for chunk number I. And then I'll pull this factor out to the side. Now, generally speaking, the square root of a quantity squared is the absolute value of the quantity. But because in our generic setup for integrals with respect to x, we always take the delta x's to be positive, I don't have to worry about the absolute value sign. So the chunk of arc length that goes with piece number I is just given by this formula. This is starting to look a lot more like what we're used to. So if I add up all of these approximate distances, I get this sum. If you remember from Calculus 1, if I look on subinterval number I, which starts at xi minus 1 and ends at xi, that'll be delta x number I. It has y coordinates yi minus 1 and yi. I'll call the vertical displacement delta y number I as I did before. Delta y over delta x is the slope of the straight line that connects the ends of the 2 points that I've got here. According to the mean value theorem, that's equal to the derivative of f evaluated at some number ci between the start point and the end point. So instead of writing this, I'm going to write this, and now see, when I take the limit, this looks exactly like the setup that we've had before. To transition from the finite sums to the integrals, the limit of sum symbol turns into an integral sign. In the thing that was adding up being multiplied by delta x number I stop writing ci or xi, or whichever letter I've used, to represent a number in subinterval number I, and I replace it with the letter of integration, and the delta xi's transform over into dx. A and B are the x values that go with the start and end of the curve that I'm looking at. The conclusion that we draw from this is if I start at x equal a, end at x equal b, travel along the curve y equal f of x, then the distance that we've traveled along the curve, the arc length as we're going to call it, is the integral from a to b of radical 1 plus the square of dy dx integrated with respect to x. Many books use the lowercase script letter s for the arc length, so I'm going to habitually do that. Now, as I said, you can do another situation where x is the dependent variable of independent variable y, so x is a function of y here. I could start at some c as a y value, end at some y value d, go through the same argument as before, and you will find out that this is the formula for the arc length. This is exactly the same thing we got the first go round, except every place I had a reference to x before, I have a reference to y, and vice versa. I'm not going to go through the entire argument again, but the reason basically is you could factor the delta x squared out under the radical sign, or Or you could factor the delta y squared out under the radical sign. And if you do that second thing, you get this expression. When you add them up and take the limit, you get the formula that I just quoted a moment ago. So there's good news and bad news. The good news is that it's easy to write down the integral that represents arc length. It's very procedural. There's no thinking to do about it now. The bad news is that we know how to integrate some things, but not others. And most of these arc length integrals that we set up, at least at the current time anyway, we don't know how to find an antiderivative for. That leaves us in the position of either leaving it in integral form for the answer, or we could use the numerical integration routine that's built into the calculator. If you're not familiar with that, I'm going to illustrate it shortly. For example, suppose that I want to find the arc length along the curve y equals x squared, starting at the place where x is 1 and ending at the place where x is 3. In our formula, we need to know the derivative of y with respect to x, which is 2x. The quantity that's going to go underneath the square root sign is 1 plus the square of the derivative, so that'll be 1 plus 4 times x squared. The arc length is going to be the integral from 1 to 3 radical 1 plus 4x squared integrated with respect to x. Not to insult anybody's intelligence, you cannot write that as the square root of 1 plus the square root of the other thing. The arithmetic doesn't work. Unfortunately, this is a thing that we don't know at this time anyway, how to get an antiderivative of. So what I did was I brought out my TI calculator and used the built-in routine that approximates integrals. Unfortunately, the only ones I have with me right now are so bright that you can't really see what I'm typing, I don't think. So I'm going to wait on this and have a very short discussion some other time about how to do the integral with fn int if you don't know already. The calculator tells me that it's about 8.2681 units of length. You could also do this a different way. Y is equal to x squared, and the piece of the curve that I'm looking at is in the first quadrant, so I could equally well express this as x equals square root of y. So now y is the independent variable and x is the dependent variable. The y goes from 1 to 9, so those are going to be my limits of integration. X, the square root of y, is y raised to the 1/2 power. If you take the derivative of that, as we always do, you end up with 1 divided by 2 times square root of y. The thing underneath the radical sign is going to be 1 plus the square of that derivative. So I integrate from 1 to 9 with respect to y now. The square root of 1 plus 1 divided by 4 times y. This again is something we don't know how to integrate at this time. I did the calculator thing on it again, and naturally I got the same answer I did the other way. I have to get the same answer or I've made a mistake someplace, because the length of this arc is whatever it is, and changing how I calculate it can't change that length. That would be crazy. I'm going to look at the graph of the hyperbolic cosine function. I want to find the length along its arc from -2 to +2. This is one of the very few things that we can integrate easily. You learn about these hyperbolic trig functions in Calc 1, or at least you're supposed to. If anyone is unfamiliar with them, let me know, and we'll talk about that as well. The derivative of the hyperbolic cosine is the hyperbolic sine. So the integral that I have to do is the integral from -2 to +2, square root 1 plus hyperbolic sine squared of x integrated with respect to x. Now, there's a trig identity for the hyperbolic functions that's similar to the one for the trig functions. In the case of the hyperbolic functions, it's hyperbolic cosine squared minus hyperbolic sine squared is 1, which means that 1 plus hyperbolic sine squared is hyperbolic cosine squared. The hyperbolic cosine is always positive, so square root of hyperbolic cosine squared is hyperbolic cosine of x integrated with respect to x. An antiderivative for the hyperbolic cosine is the hyperbolic sine, and I have to evaluate that at -2 and 2 and subtract. And doing this on my calculator, I find out that the length of this arc is about 7.25372. Another example is y equals natural log cosine x. I'm going to look at x being between 0 and pi/4 radians. If you remember, on that range of x values, cosine is strictly positive, so the natural log will make sense. I've got to figure out what dy dx is. This is going to involve the chain rule. The derivative of ln is the 1/over function. So I write down the 1/over function and evaluate it at the place that the natural log was being evaluated at, namely cosine x. Then I have to multiply by the derivative of cosine x with respect to x, which is negative sine of x. Sine over cosine is tangent, so dy dx is the negative of the tangent of x. The integral that I have to do will be the integral from 0 to pi/4 square root of 1 plus, and I see people make mistakes with that negative sign all the time, so I put brackets around the thing I'm squaring. I'm going to take negative tangent of x and multiply it by itself. The two negative signs cancel out, and I have to integrate from 0 to pi/4 square root 1 plus tangent squared of x dx. We have a trig identity involving 1 plus tangent squared. 1 plus tangent squared is secant squared. So this is going to let me rewrite my integral in terms of the secant. Now, strictly speaking again, square root of a quantity squared is the absolute value of that quantity. But on the interval from 0 to pi/4, the cosine is positive, as indicated on this bad graph. The secant is the reciprocal of the cosine, so the secant is positive as well, meaning that I can just drop those absolute value signs. I have to calculate the integral from 0 to pi/4 of the secant of x with respect to x. But if you look on the big list of things we know how to integrate from Calc 1, secant of x is on the list. An antiderivative is natural log absolute value secant of x plus tangent of x. That's one of the more obscure ones, but if you go back and look, you'll see that it's on the list. I have to stick x equals 0 and x equal pi/4 into that, and then subtract. And when all of the dust finally settles, the answer comes up to be natural log of 1 more than square root of 2. I checked this with my calculator routine, and this is the correct answer. And the last thing I want to talk about today briefly is lateral surface area. Lateral means side, so I'm going to think in the first little thing about a cylinder, and I want to think about how much surface area the cylinder has around the side, the lateral surface area. I'm not going to include the circles at the ends of the things. This is just the side. So I'm going to have some cylinder, it's going to have a radius, which as usual, I'm not going to give a name in terms of letters because I don't want to make any sort of subconscious idea that one variable is always the independent variable. Also, if I did that, that would be a letter that I can't use for anything else. And it's better just to think of it as the radius is going to have a radius and it's going to have a length. I'll think of taking an X-Acto knife and slicing it right down the side and unrolling it, flattening it out. This is still the length here that I started with, and the other direction is how much distance I've got around a circle, which you'll remember is 2 times pi times the radius. Unfortunately, cylinders are not going to do the job for us because they don't take into account enough of the differences in function values as you move around. The shape that we're going to look at is called a frustum. It's almost a cylinder, except the circles at the ends are different sizes. On one end, I'm going to have a bigger radius, and on the other end, a smaller radius. Instead of thinking about the length, I'm going to think about the slant length, the length that connects the bigger circle to the smaller circle. The area of such a thing is 2 times pi times the radius times not the horizontal height, but the slant length. There's an argument in the textbook for this. I was going to make a purely algebra argument, but it got out of hand. It turns out that this is true, though. In any case, it's not important because of what we're going to do. I look at the graph of some y equal f of x, and I think of revolving that around the x-axis, much in the way that we did with our volumes in the previous sections, except this time I'm not interested in the volume. I'm interested in how much surface area there is around the sides, the lateral surface area. The game we're going to play is the same game we've played before, though. Chop the curve up into a whole bunch of much smaller pieces, pieces that are so small that I can pretend that the graph of the function is almost a flat straight line, but not horizontal, it's flat. So this is a frustum, and the reason I said it didn't matter about the radius argument is when we make the delta x very small, the small radius and the big radius are practically going to be the same thing anyway, so it doesn't really matter. The area that goes with this is 2 pi times the radius, which will be the y coordinate, which will be f of x in this problem, times the slant length. And the slant length is the arc length. So what we're going to do is going to take 2 pi times a y value times a little chunk of arc length, add them all up, and then take the limit to turn it into an integral. So 2 pi times radius times slant length. 2 pi times, in this particular circumstance, the y coordinate, that's the radius. I have to express that in terms of x, though, because we're going to end up integrating with respect to x, times the slant length, which is a little piece of arc length, which we figured out how to do previously in this discussion. Take all such things, add them up, take the limit, and as usual, it turns into an integral. We've got our 2 pi, we've got our f of x, which is the y coordinate, and this is the chunk of arc length that we have. This will turn the lateral surface area problem into a problem of integration. And just like before, you can do exactly the same thing if y is not a function of x, but x is a function of y. The radius now is going to be the x coordinate, and x is some function of y. So 2 pi times the radius times the arc length is 2 pi times the x coordinate, which has to be expressed in terms of y, times the chunk of arc length, which, if I'm thinking of y as being the variable, is radical 1 plus the derivative squared, not of dy dx, but of dx dy, multiplied by, I really ought to write delta y. I really ought to have indexes on everything, but hopefully everybody's beginning to see what the game is here. Add up all these things, take the limit, integral from the smallest y value to the biggest one of 2 pi times the radius f of y times radical 1 plus square of derivative of x with respect to y integrated with respect to y. Except for the names of the letters, this is the same result that we got previously. And lastly, I want to take the straight line y equal 2x, starting at x equals 0, ending at x equal 3, and revolve it about the x-axis. This is going to make a right circular cone of radius 6 at the base and perpendicular height 3. This is not the slant height, of course. It wouldn't help me even if it was. The derivative of y with respect to x is 2. The arc length is going to be given by radical 1 plus the square of dy dx multiplied by dx. Again, I really ought to say deltas, and I ought to have indexes, but we should be getting familiar with this game by now. Dy dx is 2. If you square that, you get 4, and then add 1. This is just going to be square root of 5 dx. So this is going to make the integral pretty easy. What have you got to have? 2 pi times the radius times the arc length. 2 pi is a constant. We know what the arc length is going to be. The radius is going to be the y coordinate. But I have to express that in terms of x because I'm going to end up integrating with respect to x. So I went in and put in y equals 2x here. Combine this 2 with the other one. The area that goes with each little frustrum is going to be 4 pi times radical 5 times x dx. And then we do the usual thing. If we had indexes on these, we would add up all the little indexed pieces and take the limit. But by now, hopefully everyone sees what's going to happen. We have to calculate the integral from 0 to 3 of 4 pi radical 5x with respect to x. Even though it's kind of strange looking, 4 times pi times square root of 5 is a constant, so pull it out of the integral. Antiderivative of x is x squared over 2. Cancel a 2 out. Evaluate at 3 and 0, and when the dust finally settles, the lateral surface area of that cone is 18 times pi times radical 5. I hope this is clear enough for everyone. I had started using permanent markers to write these with, and when I went to write this one up, the only ones I had available were fine point. I hope that this is still legible enough. If it's not, please let me know and I'll dig up some of the other type. In the meantime, I hope everyone's having a good day. We'll talk again soon.